So in this video we continue this elastic collision example that we started in the previous. We got down to this equation here, which has the unknown V2F that we have to solve for. We have 4 times 100, which is 400 meters per second, minus 100 meters per second V2F. I should say that's meter squared second squared. V2F. Then we have plus 25 times 4, that's 100. Whoops, sorry, I can't do that. 25. And then I've got to square this. Well, this squared is 16 meters squared per second squared. Then we have 2 times this times that, which will be 8 meters per second V2F. Then we have plus V2F squared. And then we have 5 times 16, that's 80 meters squared per second squared. And last but not least, we have minus 5V2F squared. Alright, so still we got an awful lot of stuff that we are going to have to do. We're going to have to start collecting some terms. So we can take the 80 from the 400, and that gets us 320. We have the 16 times 25. 4 times 25 is 100, so that's 400 more, so that would be 720 meters squared per second squared. Since that's kind of getting confusing, let me check the things we're taking care of. So taking care of that, I've taken care of this term, and I've taken care of that term. Okay. I also have some V2Fs. I have minus 100, minus 8 times 25, that would be minus 400. So combined, that's minus 500. Now let's see if I didn't do that right. 8 times 25, that's 200, so minus 300. Alright, that looks better. Whoops. V2F. So let me mark those as well. So we've done this one, and we've done that one. And then we have 25 times V2F, but then we're going to bring on the other side 5 more when they come over here. So that 5 will come onto this side, and we will get 30 V2F squared, and that should equal 0. And let's check to make sure we did this right. Easy to mess this up. You had 425 times 16 was another 400, it was 800, but we had to subtract 20, which gave 720. We had minus 100, and then we added a minus 200, that gives a minus 300, and then we had 25 of these, and we added 5 more. Alright, so that should be correct. So what we have here is a quadratic. There's A, there's B, and there's C. And now we've got to solve the quadratic formula to find V2F, the final speed of the second block. Now, V2F, some things about V2F we know. V2F is going to be greater than 4 meters per second because it's getting ran from behind by the block, the blue block, which is causing this block to speed up, and it was already going 4 meters per second. So we have that it's minus B, so 300 meters per second. Then we have a plus or minus. We have 300 meters per second. We have to square that. Minus 4AC, 4 times 30 times 720 meters squared per second squared. And all of this has to be over 2A So b squared minus 4ac over 2a. The 2a, there's the 30. So that would be over 60 on the bottom. And we will, of course, have to punch a calculator. But remember that this has to be greater than 4 meters per second. Alright? Because it has to pick up speed because it's getting pushed from the other block. Alright, so we take our calculator, 300 squared minus 4 times 30 times 720. We get 3,600. We take the square root of that answer. We get 60. Now, if we subtract 60 from 30, we'll get 240. And 240 over 60 is 4. And that's not allowed. So it can't be the minus sign. It has to be the plus. So we get 360 meters per second divided by 60, which says that the block is now traveling at 6 meters per second. The reason being is that if you took the minus, you would have got 4 meters per second, which would say this thing hit it and did not change that speed. And that's not possible. Physically not possible. There's only one speed. There couldn't have been both a plus and minus because we know there's only one speed that this thing could have taken off at, one solution to the problem. Now, it asked for the change in kinetic energy. Well, the change in kinetic energy is 1/2 times the mass, which is Rm2, times V2F squared minus V1F squared. So that's 1/2, and then we need to know the mass of the object, which was 1.5 kilograms. We have 6 meters per second, which we're going to square, which is 36, and we're going to subtract from that 4 meters per second squared, which is 16. 36 minus 16 is 20. So we have 36 minus 16 is 20. 20 divided by 2 is 10, and 10 times 1.5 is 15 joules. So the second block gained 15 joules, and its speed became 6 meters per second. And the red, or the initial block, the blue block, lost 15 joules. And we can figure out what its speed is. And I think if you do that calculation, I believe you'll find that this block actually stopped. So it smacked into the red block. The red block took off with 1 meter per second, or 2 meters per second more speed. But this blue block totally stopped. And it conserved both momentum and it conserved energy. See if you can find that out yourself. Remember, the main thing about these problems is not that they're incredibly hard. There's only two concepts. Elastic collisions, all collisions conserve momentum. Elastic collisions conserve energy. But there can be quite a bit of algebra in these type of problems. In fact, the elastic collision problems usually give you less information because you have more equations because you have two conditions. And therefore, the algebra is more intensive than on problems that you're assigned that are inelastic, because since you only have one condition, momentum conservation, they have to give you more information. So there's fewer unknowns. So you don't have the simultaneous equation problems that you have when you solve momentum and energy. One other thing, I solved this similar to the way the book would do it, which is to write kinetic energy as 1/2 mv squared. It is in fact easier usually to write kinetic energy as p squared over 2m in problems of this type. And the reason is that the total p in the momentum is conserved. And so often you can cancel things out and make the algebra less difficult. Now, I didn't say always, but a lot of times it will make the algebra less difficult. Also, it turns out that this formula has more advanced uses where this P can be generalized in advanced courses in college. So there are a couple of reasons why we prefer this form when dealing with momentum collisions. For now, if you're having trouble with these problems, let's just stick to 1/2 mv squared. But if you've mastered these, then you may want to try to see if it isn't easier in this problem to work with p squared over 2m. Maybe this, maybe it isn't. I haven't done it for this particular problem. Anyway, that's all for this video.